My voice loud and clear?
Clear.
Yes.
Yeah, thank you. um, today, I would like to apologize first. I'm actually outstation. I'm actually in KL right now. I'm attending a workshop which is supposed to end at 12 today. However, I didn't bring my, another set of camera and also my mic. But I hope it's clear enough for you. So I won't be, teaching you manually lah for calculation today, or drawing the EY curve. But I'll try to make it up to you in our next class on Wednesday. All right. Now, sometimes you also will hear some noises from the next door. I hope it won't disrupt your or disturb your learning. All right then. Let's continue with our lesson since last class. Our last class is actually I cancel last Wednesday class, so the last class will be last Sunday then. All right. Okay, we'll continue with control sections. Let me share the slide first. All right. Okay. Yeah, I need to admit. Okay. Um, Now, what is control section? In Bahasa also, it is known as keratan kawalan. Actually, once we know the characteristics at the control section, all right, of course, we need to know the flow dynamics characteristics first. For example, the discharge, depth of flow Y, and the velocity. Once we know, the characteristics of flow, of the flow as well as the characteristics of flow at the control section, we actually can calculate or find out the characteristics at upstream and downstream of the control section. That is why it is so important to know, about the control section, because you can actually get characteristics of flow for the upstream and downstream of the control section. If there's changes in flow, right, you would like to know what is happening upstream and downstream. So therefore, we normally will establish a control section first. Now, normally at control section also, critical flow occurs. Okay, so there will be changing either from subcritical to supercritical or supercritical to subcritical flow. All right. So when supercritical flow change to subcritical, okay, that means the flow is high speed. It changed to subcritical, which is low speed. Which change to low speed, there will be hydraulic jump. Means there will be jump of water lah. That means there will be bubbles of water, because from high energy flow, when it changes to low energy flow, it will involve loss of energy. Right, so those bubbles actually reduces the energy. I'm meeting people, sorry, that's why I have to change from full screen to the normal screen, because our friends are coming in. Now, okay, a control section control upstream and downstream. So you get to know, once you know the characteristics at the control section, you actually can find out what is happening at upstream and also downstream. Okay, so this is our task. We are going to analyze. All right, Once we know the characteristics of flow at the control section, we are going to analyze what is happening at upstream or downstream. Actually, we can also analyze what is happening at the control section. So this is what we are going to do. Sometimes when we do design, right, for example, bridge, where we restrict the flow of an open channel, we would like to know what is the consequences, all right, at downstream and also the upstream and downstream. So this is what we are going to learn today. Now, example of control section. Just a second, I need to admit. Okay. The example of control section here, if you look at, we have flow. These are the examples of flow occurrences where there will be control section. If there is a channel with uniform flow, that means you won't have control section, right? Only there's changes between subcritical to supercritical and subcritical, or there will be changes in depth of flow. You can actually have a control section there because there's a transition, right? So therefore, there's a critical critical flow point there. If you look at the first diagram on your left, is flow from mild slope channel to steeper channel. And then on your right, you have, discharge from a mild slope channel into a pool of water. It could be, depression, or even any pond or anything lah, all right? Not necessary pool. Now you also have free overflow, all right? Of course, you have the velocity after the overflow is equal to square root GH lah, all right? It's actually free fall, and then you have reservoir water. That means from the pool of water is draining, okay, down a slope. This is a spillway lah. Example, we have spillway. Later on, we are going to learn about spillway. Spillway means, water spilling on the way, on the channel lah. That's why we call it spillway. And then we also have flow through sluice gate. This is the sluice gate. If you see, just a second, I need to admit our friend. Okay. All right. So this structure here is the sluice gate. Of course, this is the longitudinal section. If you look at the front, right, the cross section, you can see a door lah, right, where you can adjust the opening. This is the opening here, right? So it actually can create supercritical and also subcritical flow lah, depending on the opening. In this case, right, since there is a jump, all right, this is known as hydraulic jump as well. Therefore, in order to create this hydraulic jump, the condition would be the upstream should be supercritical and the downstream is subcritical. All right, so there will be a jump. On F, all right, on your right is flow over spillway. This is actually dam-like structure. So you have flow over spillway lah, all right? So this is your spillway here. And then you also have flow over broad crested weir. This is your control section, all right? The one, if you look at the red dots, right, those are the point of control section. Normally, this is the point where critical flow occurs. In this case, you have subcritical changes to supercritical flow, right? So during the change, right, of course, there will be a critical point, all right? From sub to super, of course, it will go through a critical stage. In this case, you have flow through constricted channel. Okay, this is the longitudinal section. And this is actually the plan view. That means you are looking from the top. When I say constricted means the width, look at this. The width initially is, let's say this is B naught, okay? This is B naught as well. At this location here, B naught becomes B, smaller. It is being constricted. So therefore, this is the case. we are going to look at this case as well, all right? And also this. So in this chapter here, we are going to analyze what is the depth upstream, on, above the weir, downstream, and also upstream on the at the construction, and also downstream of the construction. So we get to analyze the depth of flow, the velocity of flow, if you want to know, okay, and also, all right, basically those are the characteristics, right? And also, of course, you can actually get the specific energy too. If there's no energy losses, the specific energy will be equal at all points. All right. Wait now, I need to admit. All right. Okay. This is what
to control the level of water in the river.
Are you able to hear the sound?
Mills relied on water power.
Are you able to hear the sound?
Yes, can.
Okay.
To drive saws, grinding wheels, and other equipment, rivers are in level. So how can we flatten this curve? Of course, this could only fit a certain length of weir within a fixed footprint. That's not completely true.
Doctor.
You can actually fold a weir to get more length.
Doctor, slide no change.
I'm sorry?
Screen dah tukar.
Oh, tak dapat tengok screen
Yeah.
Oh, sorry. Thank you so much for informing me. Alright, just a second. I'm going to stop presenting. I'm going to share the whole entire screen. Okay, I'll start.
Being able to control the level of water in a river is beneficial in quite a few ways. Historically, mills relied on water power.
Okay, are you able to see the screen and hear the voice? The sound?
Yes.
Okay, great, thank you.
Drive saws, grinding wheels, and other equipment. Raising the water level in a river can also allow boats and ships to navigate areas that would otherwise be inaccessible. Finally, having control of a river can help mitigate the damaging impacts of flooding. But how do we get this type of control over the level in a body of water? Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about weirs. This video is sponsored by Skillshare, the best way to learn a new skill online. More on that later. A weir is a small dam built across a river to control the upstream water level. Weirs have been used for ages to control the flow of water in streams, rivers, and other water bodies. Unlike large dams, which create reservoirs, the goal of building a weir across a river isn't to create storage, but only to gain some control over the water level. Over time, the term weir has taken on a more general definition in engineering to apply to any hydraulic control structure that allows water to flow over its top, often called its crest. In fact, the spillways of many large dams use weirs as control structures. So how do they work? If you watch my previous video on the basics of open channel hydraulics, you'll remember that for subcritical flow, that is, slow, tranquil flow seen in most rivers, the depth is controlled by downstream conditions. That means adding a weir across a river will increase the water level upstream. But by how much depends on the flow. This is the equation for flow over a weir. We're not going to do any calculations here, but it's important to know the factors that govern the performance of our hydraulic structure. This equation says that the amount of flow that passes over a weir depends on three factors: the length of the weir, the height of the water level above the crest of the weir, and this coefficient which changes depending on the geometry of the weir. The graph of a hydraulic structure's flow versus water level is called its rating curve, and this is the rating curve for a typical weir. In many cases, a weir is a passive structure, meaning that once it's installed, there's no way to change this rating curve. And that's not always ideal. Streams and rivers are subject to tremendous variability in flow rate. A hydraulic structure may normally flow a small amount, but in flooding conditions be asked to pass incredible volumes of water. With a passive structure and fixed rating curve, that variability in flow means tremendous variability in the water level upstream. During the flood, a weir may back up water badly enough to cause damage upstream. If you're using a weir for a spillway on a dam, you might have to build your dam much higher just to handle the water level that occurs during very rare but extreme cases, increasing the overall cost of the structure. Ideally, hydraulic structures used to control water level would have a flat rating curve, meaning over a wide range of flows, you only get small changes in level. So how can we flatten this curve? Going back to the weir equation, there are only two other parameters available to increase the flow for a given water surface. We can improve the geometry of the weir to increase its efficiency. Different shapes of weirs can pass flow more efficiently and thus have a higher discharge coefficient, but this has a practical limit. The most efficient shape for a weir is to match the curve that the water would take off the sharp crest. This part of the flow is called the weir's nap, and the shape that matches it is called an ogee. With ogee-crested weirs, we can get discharge coefficients as high as around 4, but that's pretty much the limit. The other parameter we can change is the length of the weir, but in many locations, the available footprint for the weir is a fixed size that can't be increased. Even if the footprint isn't fixed, increasing the length of the weir can add significant costs. Of course, this challenge is easy to address if we allow for structures with moving parts. Many dams and spillways have large gates or valves to control flow. There are a wide variety of types of controlled outlets used on hydraulic structures, including crest gates that act like weirs that can be raised or lowered. The benefit is that the structure's capacity can be increased while flows are high by opening gates, and then decreased when flows return back to normal. Controlled structures provide more flexibility in how water gets released or held back, essentially turning a static rating curve into a family of curves that can be selected from to meet operational goals. Of course, controlled outlets come with a major disadvantage of increased complexity, and in many cases, requiring an actual person be available 24/7 to open gates and make releases based on inflows. So what if we could get the benefit of a controlled outlet without the disadvantages of increased complexity and operational obligation? Well, there's one more trick that hydraulic engineers have up their sleeves. Remember when before I said you could only fit a certain length of weir within a fixed footprint? That's not completely true. We can actually fold a weir to get more length within a given space. This is called a nonlinear weir, and it's used in situations where you want greater discharge within a given footprint, but without the need for actively controlled outlets. To show how this works, I built this flume and some model weirs. This first weir just goes directly across the flume, no bends. I'll mark the water level in the flume, first using a straight weir. Now, with the same flow rate, I'll replace the linear weir with the folded version. This has just about twice as much weir length in the same footprint. You can see that even though the weir is passing the same amount of flow, the water level upstream is lower, almost half the distance to the crest from the original level. We flatten the rating curve, allowing for greater discharge at a lower water level. Nonlinear weirs with folded cycles like this are called labyrinth weirs, and they're becoming more common as hydraulic control structures. There are also rectangular versions called piano key weirs. It's easy to see how beneficial weirs can be, from generating power to improving navigation, controlling flooding, and even acting as the spillways of dams. With all those benefits, there are some downsides as well. Impoundments across rivers affect the aquatic environment. Low-head dams can also pose a serious danger to swimmers and boaters, a topic I'd like to discuss in the future. In fact, many old weirs that are no longer needed are being replaced or completely removed to restore the river to its natural.
Okay, sorry Faisal, I have to admit you later because I'm showing the video just now. I hope you get some idea about the importance of analyzing the depth of flow upstream, above, and also downstream of the weir. Because actually, when you place a hydraulic structure such as a weir along, obstructing the flow, it will change the hydraulic characteristics of the flow. So that is what we are going to analyze lah. Okay. And all right, this picture is actually showing the labyrinth or It is more of a labyrinth weir in Putrajaya. Just as the video has already explained earlier, it actually increase the length of your weir. And actually it can, if you, if you notice just now, it says it actually reduce the level of water depth upstream of the channel. When I say reduce means comparable to when you have a straight weir, okay? But of course, in this case, when you put up a weir, definitely you are going to increase the depth of the upstream of the weir. But the difference between labyrinth and also the a straight weir is labyrinth has smaller depth of flow. That means it's going to increase at a smaller depth compared to a straight weir. All right. So these are, you can actually look at this in Putrajaya. I actually went to Putrajaya. I've seen this. There's a restaurant next to it lah. I forgot what name already, at Warisan or what. Okay. So these are actually, if you notice, right, everywhere you go, right, even through highway, you notice, your drainage system left and right, and then on the cut area, field area of your hill, you also will notice all these hydraulic structures. It's just that once you know what the functions are, you will be more appreciative of those hydraulic structures, right? Now, as I told you earlier, we are going to look at two cases. One would be the flow over broad crested weir. The other would be flow through constructed channel. That means the width of the channel is going to get reduced lah. All right. There are cases where the width had to be reduced. We'll look at this first, which is a flow over broad crested weir. Now, of course, flow in a prismatic open channel is uniform if there's no obstruction. Okay, it will just flow as uniform as it is. But if you install a broad crested weir, it's going to change from uniform to non-uniform. It is going to, well, how does it change? What is the depth of flow, resulted by the installation of the weir? It depends on the height of the weir. If you look at this diagram here, all right, this is your broad crested weir, right? And the height of the weir is denoted by the symbol of H, all right, which would represent the height of the weir. Now, if you didn't have this weir installed, of course, the flow would be uniform flow lah, where you are going to have why not depth of flow. Now, this depth of flow, which is located at 0, right? Why not, right? It probably would be very far away, which is not affected by the installation of weir. This is denoted by why not, which is the depth of uniform flow. Now, just behind the weir, which is upstream of the weir, the section is known as 1. So it is denoted by, the depth of flow is denoted by the symbol of Y subscript 1 or Y1 lah. The depth above the weir is Y2. Downstream of the weir is Y3. I hope you are clear. So now I'm introducing why not. Of course, why not is the one we have learned in chapter 2. So in chapter 3, we get to know where's the location of Y1, Y2, and Y3 in the cases of broad crested weir as well as flow through constructed channel. Now, these are some of the type of weirs. We have sharp crested. Sharp crested means look at the crest. It says sharp crested. That means the crest is short, okay, and sharp. Now this is broad. All right, there's a criteria on how to classify. It is in the subsequent slide. I'll show you the criteria how it is known as broad crested. This is sharp as well. This is sharp plate. This is sharp as well. But there is a criteria. We are going to look at this later. So this is known as broad. Now in this case, we are looking at this broad crested weir here. All right. Just a second, I'm going to go faster. This card. Let's see if I can go faster. Alright. Okay, now look at this. If you put a broad crested weir, right, you are going to have changes in depth, upstream, above, and downstream. This is from, the flow is from right to left, Okay. So you have learned about nap, right, just now, which is the thickness of water. This is a nap, right, going through. Okay. See, if you block the downstream, you will have backwater lah. Okay. Now this would be submerged completely now. Okay. So there are things that, this is in laboratory, which they are, actually this is a flume lah. Flume is, that means open channel flow above the ground. It is conducted in lab, but in reality, you are going to have cases like this as well. Of course, it's not a block of wood anymore. You probably have, a stretch of rocks, log, and so on, right? Or purposely built weir. So I'm going through, I'm going to share the link afterwards for all this video. It's available at YouTube as well. So let's continue with our lesson. Here's the thing. Now, just always, I mentioned that, the depth of flow upstream, the changes to the depth of flow upstream, above and downstream of the weir is actually influenced by the height of the weir H. Now, let's see. Now, on this slide, I'm introducing H mean, which is the minimum height. Now, what is the definition? It's minimum height. H mean, minimum height of weir, which will start to produce critical flow depth above weir. Okay. Now, look at this. That means if H is equal to H mean or greater than H mean, Y2 would be YC. Okay, look at this. You see, we actually classified this into 3 categories. The first one, when the height of the weir is less than H mean. Then, second case, is when the height of the weir is equal to H mean. So Y2 equals to YC. In third case, case 3, so we have case 1, case 2, case 3. Case 3 is when the height of the weir is greater than H mean. So your Y2 remains critical depth. Based on this definition here, what is H mean is the minimum height. So if it's greater, the flow is still critical at above the weir. Alright. So Y2 is YC and E2 becomes E mean. Remember the EY curve, right? When Y is YC, your E is E mean. Alright. Now, don't worry about this yet. I know it's a bit you probably find it a bit complicated. As we go along, we do exercise, you understand this better, and when you come back, you know what is what. Okay, but I'm just going to go through a bit. Okay, how are you going to read this chart here? Look at this, the condition. This is case 1. That means case 1, you have subcritical, supercritical. Okay, so on the left diagram, it's all subcritical. Case 2, case 3. By now, you should know already what is case 1, what is case 2. Case 1 is when the H is less than H mean. Case 2 is when the H is equal to H mean. Case 3 is when H greater than H mean. And then on the right side, here you have a set of supercritical. It's still the same. It's divided into case 1, case 2, case 3. I hope by now you should know how to classify subcritical and supercritical. Subcritical is when the depth of flow greater than YC. Supercritical is when the depth of flow less than YC. I told you having a constant slope, right? If you have a constant discharge, if you have very steep slope, okay, it's going to flow fast. That's why your depth is going to get thin. Because Q equals to AV, right? Of course, your A is smaller lah. Provided since your B is fixed already, so what changes? Your Y will be small. The same thing, all right, for subcritical, all right, since you are expecting lower V velocity, so therefore your depth is greater lah. Okay. What else? Of course, if you in the case of subcritical, you see the depth of flow is greater than the supercritical. The red dashed line is actually the depth of critical flow, right? So it shows that the blue surface, a blue line surface is in this case is supercritical and this is subcritical, right? Now look at this case 2 and case 3 at location Y2, right? This depth of critical flow and the depth of flow is equal. So therefore, it's just to show that, you know, Y2 is equal to YC in both subcritical and supercritical cases. And for case 3 as well, Y2 is equal to YC. Now, another thing I want to explain here is, look at this. Y1, Y3. That means upstream and downstream of the weir. Case 1, case 2 remain the same. Y1 equals to Y0, Y3 equals to Y0 for both conditions, as well as case 2. Y1 equals to Y0, Y3 equals to Y0. However, for case 3, it doesn't matter, right, regardless of whether it's subcritical or supercritical. When it's case 3, that means the height of the weir is greater than H mean, your Y1 is increased greater than Y0. All right, and it is in subcritical. Y3 is in supercritical in both cases, in both states of flow. That means regardless of either is subcritical or supercritical flow, when it's case 3, your Y1 would be greater than Y0. Your Y1 is in subcritical flow and your Y3 is definitely going to be supercritical. Don't worry yet, okay? As we go along, you understand this further. Now, this is another diagram that I purposely drawn because the diagram earlier is not very clear. This actually shows the same thing, except that just now you have, you know, the cases classification on your left, right. Now I put it on top. Okay, the condition just now is on the top right. Now I put it on the left. Okay, it's the same. It's just showing another configuration. All right, I'll just skip this first. Okay. Now, the cases of where there's backwater, in this case is case 3. It doesn't matter whether it's in subcritical condition, this is known as backwater. That means when it's too much water, okay, and you know, the height of the weir is greater than, and the condition would be when the height of the weir is greater than H mean, you are going to have backwater here. Backwater means, now what is the issue about this backwater? Now in this diagram here, you probably say, okay, it's not going to affect much. But you never know if it involves a wide area, this length of backwater might extend few kilometers away. And what would happen is cases like this. This is backwater flooding, okay, near the river bridge. It will cause this flood is caused by backwater when the river, okay, is filled up with backwater, it spill over and it flood the entire area. So this is what we are trying to avoid. This is where you comes in. All right, as the hydraulic engineer, you are going to analyze, make sure this doesn't happen. Of course, sometimes you cannot avoid it. But of course, you will inform, the authority at which discharge or what kind of rainfall will cause this condition. Of course, you are going to list out lah. Okay, you can't really avoid, flooding and things like that, but we can reduce the effect and such, the impact lah. All right. Now, we are going to steps, all right? We are going to look at steps to analyze flow over broadcast area. Now, I've actually put up this slide to help you easy to analyze, the problem of flow over broadcast area. Now, first thing is, we would try to find out what is the depth of uniform flow and the depth of critical flow. Sometimes the question gives you all this, so you don't need to find Y naught and YC. Why we want to know Y naught and YC? We want to know, whether, if the question asks whether it's subcritical or supercritical, of course, you definitely have to do Y naught and YC. Now, sometimes we want to find YC because from YC, we can actually get E mean. Okay, because if you want to find H mean, you need E mean. E mean and E naught. That's why you need to know Y naught and YC. Alright? But you don't have to categorize it, whether it's subcritical or supercritical. It depends, alright? It depends on question. But that is the first thing that we need to find, Y naught and YC. Then, second step, okay, when you are analyzing flow over broadcast area, is you want to know what is the value of H mean. Why do you want to know value of H mean? Once you know the value of H mean, okay, and if the question already give you the H, you can actually classify them whether in case 1, case 2, or case 3. Because for case 1, you know that Y1 equals to Y3 equals to Y naught. Y2 is not YC. You have to find Y2, all right, based on your E naught lah, and also H. And then for case 2, Y2 is YC, Y1 and Y3, Y1 equals to Y3 equals to Y naught. For case 3, Y2 equals to YC, Y1 is not equal to Y3, is not equal to Y naught, but Y1 we know is going to be in subcritical condition, and Y3 is we know that it's going to be in supercritical condition. Right. Now, after that, after you have calculated, after you have find out what is the H mean, of course, if the question already give you H mean, you don't need to calculate H mean again lah. Right? You can straight away use the minimum height of wave. Now, the next step is to find out Y1, Y2, Y3. Of course, it depends on the cases. Just now I told you. Case 1, case 2, case 3, right? You can actually find out what is Y1, Y2, Y3. This is actually I explained earlier. Okay. Now, most probably what I would like to explain here would be how can you find Y1, Y2, Y3? Now, for case 1, you have subcritical, you have supercritical. Okay, after. Now, we know that the lower limb here is supercritical condition. The upper limb here is the depth. All right. So any point on this upper limb here of the curve is actually points for the depth that represents depth of subcritical flow. All right. So any points on this lower limb of this curve here, EY curve, it is actually the depth for supercritical flow. Now, that is why we actually try to find out Y naught and YC as well, so that we know which limb this depth belongs to. Now, for case 1, Y1 equals to, this is 1, equals to Y3 equals to Y naught. That means Y1 equals to Y naught and Y3 equals to Y naught. But what is Y2? We don't know, because Y2 is not equal to YC. So Y2, how are we going to find Y2? look at this EY curve. Actually, when I solve this flow over broad crested weir, normally I'll draw out this EY curve. Because I actually don't memorize the formula, I'll just look at all this. Is it? I wanted to find Y2. This is Y2, eh? I need to know E2 first. Because from E2, I can find Y2. I hope you still remember your formula of E. Alright, E equals to Y plus, for rectangular, is Q squared over 2GY squared, right? Okay, sorry, 2GY squared. Okay. Now, once you have E, you can actually find Y. Of course, provided you know your Q as well lah. Okay. Now, what is this E2 here? Look at this. We know that there's no energy loss. So basically, if you look at this diagram here, all right, this diagram here, your E2 is actually equals to, your E2 is actually equals to E2 is actually E naught minus H. So this is your E2. So you have E naught, alright? So this is E naught, E naught minus E2, you are going to get H. Similarly, if you want to find E2 is E naught minus H, you are going to get E2 lah. That's the formula. So you can draw it out here, okay? To find E2 is E naught minus H. Now, to find E min is E naught minus H min. Normally, if you have Y naught, you already can find E naught using the same formula. That means you just substitute Y naught, you are going to get your E naught. E min, once you have YC, you can find E min, which is 1.5 YC, right? Okay, so therefore you can find your H min. Depending on cases, all right, that means you are going to compare your H, the height of the weir that you install, compare it with the minimum height of weir. If it's less in case 1, therefore you can find your Y2. That means your E2 is equal to E naught minus H. Then you substitute, you can find your Y2 here. That means this will be E2, 2, and 2 lah. All right. So the concept is very simple, actually. Now, similarly, for supercritical condition as well. Now, what is the importance why we differentiate, subcritical and supercritical condition? Now, here's the thing: if you are using E2, right, this formula, you are going to get two depths, the alternate depths. I hope you still remember. One solution would be, the depth in supercritical, which is this location here, and another one is the depth in subcritical. So of course, if you are going to solve this subcritical condition, the right answer would be this Y2 in subcritical condition. Where if the initial condition, the E naught is in supercritical, right? The changes would be, because it never changed, right? It never reached YC yet. It's still, in this case, look at this. It's still in supercritical condition. This one also in subcritical condition. So the right answer, right, for case 1, when the outstream is supercritical, would be your depth would be in supercritical state as well. Be careful, Don't give me answer when the initial flow is supercritical, but you give me Y2 in subcritical. It's different, It's wrong. Okay, I hope you are clear. Of course, when we are working on the exercises later, we'll improve our understanding on this. Now, for case 1, right, these are the formula. Actually, this is the formula that we provide. We help you to, do calculation easier step by step, easier to help you all right. Now, how do you calculate Y naught? We have learned to find the depth of uniform flow. We are using Manning and also Chasey equation that we know in chapter 2 already. Okay. Now, how are we going to find YC? of course, in chapter 3, early of the chapter 3 already, find out what formula. For all section, including rectangular, we are using this formula. Okay. For rectangular, we can simplify that formula into this. Okay. But I don't mind if you try to find YC using this formula for rectangular channel. It's still correct. You get the same answer. Okay. Now, this is a simplified version for rectangular section. But if you want to use this for rectangular also, no problem. You just have to times B. But sometimes the question doesn't give you width of channel, or they just give you the discharge over unit width. So you still have to understand this. All right. Now, then after you calculate Y naught YC, it's the same as the procedure that I've shown you, the stages. But this one involves formula, the formula that you are going to use. Find H min is, remember just now the formula is H min is E naught minus E min. This is H min. Okay, we go back here. Look at this, E min. All right, E naught minus H min. You'll get E min. It's basically E min plus H min is E naught lah. All right. Okay. So to find H min is E naught minus E min. Okay. Then after that, find Y1, Y2, Y3. Now for case 1, Y1 equals to Y naught, Y3 also equals to Y naught. That means upstream, downstream of the weir is not changed. The depth of flow do not change. Okay, downstream and upstream, they do not change. That means the depth remains the same. It's not affected lah. Basically, when the height of the weir is less than H min. So it doesn't affect upstream and downstream. Now, therefore, you can use this formula to find your Y2. Now, where did you get your Y2 is, you need to find E2 first. Okay, E2 is equal to E naught minus H. Okay, from this EY curve already, you can see E naught minus H, you'll get E2. All right. So therefore, you substitute E2, Q, right, and of course B lah. All right. In this case, you'll get Y2. All right. Depending, again, depending whether it's subcritical or supercritical, you have to give me the depth in the right state of flow. For case 2, all right, is where H equals to H min. All right, case 2 is where H equals to H min. So straight away, okay, sometimes the question say, determine the depth of flow upstream and downstream for the case when H equals to H min. That means it's straightforward. It is case 2 already. You don't need to find H min already. Okay, because it already stated that the height of the weir is actually H min. So straight away is case 2. Okay, in this case, the same thing also. Your Y1 is equal to Y naught. Your Y3 also equal to Y naught. But your Y2 is equal to YC. That means this is the minimum height of weir that will cause critical flow above the weir. Okay. Now, so regardless lah, right, of whether it's subcritical or supercritical, your Y2 is YC. You'll get the same, right? Okay. Raise your hand if you have question. Meanwhile, in the middle of my teaching, now for case, this is case 2, this is the formula lah. All right, it's similar to the previous cases. Okay, so basically the one that changes will be this guy here, H min equals to E naught minus E min. Okay, and then you determine lah. All right, Y1, Y2, Y3. Okay, so Y2 is equal to YC. Now for case 3, Y1 would be equal to subcritical depth of flow. Y3 is supercritical depth of flow. Okay. If you look at it, doesn't matter whether it's subcritical or supercritical. Still Y1 is actually in subcritical. Y3 is in supercritical. Okay. So you need to consider the upper and lower limb lah. That means the state of subcritical and supercritical flow. Now your Y2 is simple, which would be equal to YC in both cases. Now, how do you find your E? There will be new E, alright, which actually in your specific energy would increase, alright, to E13. You have a prime symbol here. It shows it's the new specific energy, alright. That means it's not. There will be changes to E naught lah. Okay, you need to increase it so that it will pass through. Alright, you will give more energy so that the water will pass through above the weir. Now, how much? By how much? Here's the thing. If you are using E naught, right, you minus H which is greater than H mean, you are going to get point somewhere here. Alright, you know, somewhere out of the curve. So you won't have the same, you won't have flow. That no flow will occur. So what you are going to do is, you have this E min, the minimum specific energy. Alright, you consider this H which is greater than H min. Alright, so therefore the flow itself would have to increase, would have additional specific energy to make it, you know, to make sure it go over the weir. Therefore, you are going to have the new specific energy which increase from the original specific energy, the initial specific energy. So by how much is E min plus H? So the formula is slightly different from the previous one. In this case is, of course, E min plus H, you are going to get E naught. For case 1 is E naught minus H, you are going to get E2. But in the third case, if you have E naught minus H min, right, you won't get any flow, right? If, you know, everything falls on this line, there's no depth of flow, right? You need to find the depth on this line here, all right? This is the line, you know, have with the constant Q and all right? So what you have to make, you want to make sure that, you know, the minimum specific energy, so that it's not, your specific energy is not less than the minimum specific energy to make sure the flow occurs. So you have to add extra energy. So therefore, the formula would be E min plus H. All right, so you are going to get additional, which is E13 prime. What? Well, E13 means E1 prime, all right, would be this point here, all right, will give you the depth of Y1. E13 will give you the depth of Y3, but it's the same value of specific energy, except that it's going to give you alternate depths. All right, one depth in subcritical and the other one is in supercritical condition. So these are the formula for case 3. The other remain the same, except for in this case where you have you know, E13 would be E min plus H. Therefore, you need to find, you know, using this E13, you can find Y1 and Y3, like the new one. You have the symbol of prime, right? It stands for new depth of flow, lah. All right. Okay. Now let's look at one exercise. I'm going to stop after this as activity. You try out. I've given you exercise for assignment for chapter 3. You can try it out. I think there are only 2 questions for your assignment 3. One would be in you know, flow over broadcasted weir, and the other one is flow through constricted channel. So you probably want to try that out. Okay, let's look at this activity 3.10. Don't worry, I think next class I'm going to go through this again so that, you know, I can actually scribble on a piece of paper and then show it to you how the calculation works. You have flow of 10 cumac, right, in a rectangular channel of 4 meter width. The Manning roughness coefficient is 0.01. The longitudinal slope is 0.0075. Now, the height of the weir is 0.92. Here's the thing. In this question, all these are given. Even the height of the weir is given, but you don't know. Is this increase 1, 2, or 3? So you need to find H mean. Okay? And of course, in order for you to find H mean, you need to know E naught. To find E naught, you need to find Y naught. You also need to find the minimum specific energy, which is E mean. In order to find E mean, you need to know YC first. Okay, so you can find Y naught, YC first, then you can find the E mean and E naught. So we are actually following the steps that I've shown earlier. So the question asks, find the depth of flow on the weir. That means the question asks you to find Y2. So we have to establish which case it is. We know that for case 2 and 3, Y2 is YC. But for case 1, we need to find the E2 to find Y2. So let's go through this. Okay, now find Y naught and YC. This involves rectangular channel or rectangular section. So we can use the simplified formula for rectangular section. Now to find Y naught, since Manning roughness coefficient is given, you can use the Manning resistance flow equation to find Y naught. This is actually the simplified version for rectangular, where we actually take out the B already. So this is initially is Q, which is actually you have this is, sorry, let me write here. Okay, all right. The same thing, right? This is supposedly to be A equals to BY, right? So when you divide by divided A by B, you are going to have 1. This one also, when you are divided by Q divided by B, you are going to get discharge over unit width. So that's why your section factor is actually the simplified one, right? As well as this term here. Okay, now you can find Y naught already because discharge is provided. You can actually the area, the hydraulic radius, all is provided. Can you get it? Yes, you can try, because this area and method parameter, you have to write it in terms of Y lah. Then you can solve this. Okay. We have learned about this already. We can use the try and error method using the calculator to solve it. All right. So Y naught, the depth of uniform flow. Okay, now please try out this question. I don't know whether my calculation is correct or not. Okay, if it's incorrect, please correct it. Let me know. So what the answer that I got for this question is the depth of uniform flow is 0.6804 meter. Now, depth of critical flow is cubic root of Q squared over G. Okay, so this is a simplified formula for rectangular section. I got YC 0.8605. Can I have Faisal? Faisal, are you there, Faisal? Faisal Mubarak, are you there? Okay, if you are not there, can I have Shuhada there? Shuhada, are you there? I think no one is in the... Wait, I'll check. Okay. Atira, are you there, Atira? Atira? Semua dah keluar. Shuhada?
Yes, sorry.
Okay. All right, Atira, my question would be, you already have Y naught and YC, right? What state of flow, initially, what state of flow it is, the Y naught? The Y naught is in subcritical or supercritical state of flow?
Super.
Why?
Because Y naught is less than YC.
Correct. Okay, thank you. So
Alright, sorry for late responding.
Okay, no problem, no problem. Okay, I'm just worried you guys, all of you go to the restroom simultaneously. Yes?
Doctor,
Yes.
I tried to calculate the why not. I get different value.
Could you show me the calculation? I'll try to correct it if possible. You can WhatsApp me personally. But,
Okay, Doctor. Okay. Okay.
because I think, okay, is there any difference here? But okay, don't worry, let me know later because okay, if I'm going to respond to you maybe later after I travel back because after this I'm going to travel back already. Okay. Now, okay. Now you guys, if you think you have different answer, you can personally WhatsApp message me. Okay, PM me. Show me snapshot your calculation. I'm going to check whether yours is correct or why there's difference lah in answer. Okay. Now YC is 0.8605. Okay, Atira is correct. This Y naught is in supercritical state of flow. Okay. Now the next step would be to calculate H mean. Okay, by now you should know. In order to get H mean, you need E mean and E naught. E naught is Y naught plus Q squared over 2G Y naught squared. E mean is 3 over 2 YC. Alright, for rectangular section. Now, if you want to find E mean for other section than rectangular, you are still using the same formula. Oh, sorry. You are still using this formula. That means you want to find E mean. This would be YC. Alright, this will be YC. Alright, therefore you can find E mean. But we actually have shown that, we can reduce for rectangular section, we can reduce it to 1.5 YC. Okay. So for other section, you still need to use this, specific energy formula. Right? This is universal for which condition it is. So therefore, you already get E naught and E mean. All right, you substitute, you get this. All right. So your H mean is E naught minus E mean. Okay. So now by right, okay, you should know E naught is greater than E mean because it's already E mean, the minimum specific energy. It won't get lower. Alright, if it's lower, then there's no flow already. So E naught should be greater than E mean, and of course there will be H mean lah, value of H mean. So H mean is E naught minus E mean is 0.078 meter. Now the question, alright, give us H equal to 0.92. That means it is in case 3 because our height of weir that we are going to install is actually greater than the height of the minimum, that will cause the minimum height of weir that will cause critical flow above it. So it's in case 3. So it's hydraulic jump. Yeah, hydraulic jump will occur. Now, why I say hydraulic jump will occur? The case would be when there's hydraulic jump is when the upstream flow is supercritical. Remember here, actually we are going to learn about weir in chapter 5. In chapter 4, we are going to learn about hydraulic jump. Because in chapter 4, we are going to learn about rapidly varied flow and gradually varied flow. Now, hydraulic, the condition to where hydraulic jump occurs is when the upstream is supercritical and the downstream is subcritical. So in this case, our Y naught is supercritical. Now in case 3, right, remember this, Y1 would be subcritical. So from Y naught supercritical, it changed to subcritical at Y1. Therefore, there's hydraulic jump because hydraulic jump will actually involve energy loss. So therefore, for case 3, provided upstream is supercritical, you are going to have hydraulic jump. Okay, now straight away, case 3, you know that for case 2 and case 3, right, Y2 is equal to YC. So the answer, Y2 is equal to YC, which you have found earlier, 0.8605 meter. That's all. Now, can I continue? going to, show this calculation. We are going to do it together lah. Okay. I'm not going to assign yet for this case. Wait. But maybe next Sunday, I'm going to assign who's going to solve this after I show activity 3.11 first. Is that okay, guys?
Okay, Doctor.
So activity 3.11, I'm going to go through with you lah together. I guess I need to stop here actually. Okay, I need to leave already. So I'll see you on next Wednesday. Okay. I have few minutes for question and answer if you have anything to ask me for during this class. Anyone? You are clear for today's class? Guys? Oh, thank you, Iqmal. Sorry, tadi sebenarnya saya tengah ada kelas kan, jadi saya tak perasan. Saya dengar orang nak masuk tapi saya put on video kan, jadi susah nak berhenti. Okay, now I have posted the attendance link. Please fill out your attendance, okay, through the link. So I'm going to see you next Wednesday then, alright? Take care, guys.
Alright, Doctor. Thank you.
Okay, thank you.
Thank you, Doctor.
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 Thank you.
Thank you, Doctor.
Thank you, Doctor.
Bye.
Thank you, Doctor.
Thank you. Thank you.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank